The first order of business is that, I give this usually, this is sort of about order, disorder. So I have a little questionnaire basically as to which has the most order. Say you have 5 chairs in a room, which you could imagine these 5 chairs. You could stack them on top of each other. That's part 1. You could line them up in a row like they are now. That's option 2. You could put them in a circle. That's option 3. You could put 3 chairs on the bottom and put 2 chairs on the top, sort of like a wall. That's option 4. You could put them in the room like the numbers 5 on a die, like our die. That's just put them around the room like in a pattern of 5. And option 6 is random. That's just put them anywhere. So I'll try to pass this around. You can make an X or a check if you don't like X's. Whichever one you think has the most order, try to put the check down there. And we'll see what happens. Okay, so to get to the start here, I have an outline somewhere. Whether I can find it or not here. So this is measuring discrete symmetry extended, and it's a continuation sort of last year's talk, but it won't have, it's only one section that's basically extended from that. However, this is sort of what you might call the search for energy, and that's like a synonym or another name for order, basically. So this was started by H.T. Odom, is a Florida researcher who worked with wetlands and so on, and they came up with an idea of measuring order based sort of what he called emergy, something like something emerging out of energy that's built up over the past. And they have 20 pages of tables, so as far as connecting to the real world, you can look at those 20 pages of tables and it has the emergy of almost anything like sand or hogs or whatever you might think of. Like people, how much energy does it take to make a PhD person versus just someone who graduates from grade school and so on like that. So that's one way of trying to measure this. There's like 4 different ways of trying to measure this sort of unknown quantity called emergy. There was an Italian named Giannantoni who, first of all, Odom considered that an equation was transformity times energy equals emergy. So there's sort of like transformity is a scaling factor that goes from energy to this unknown order thing called emergy. And an Italian named Giannantoni suggested trying to factor this into a generative component and a dissipative component. So I gave one talk on that at the Florida Talks on Lego blocks, where the generative component is measured with symmetry like I did last year. And the dissipative component is measured by how many sides of the Lego blocks are used up. So you have like 20 Lego blocks. You can put them together and make a rectangle. You're using up a certain number of sides in doing that. So you can count that, and that's basically the dissipative. So the actual quantity emergy is based on the product of that. So if you just put a lot of blocks around the room in a symmetric pattern like the 5 pattern, you'll have a lot of generative symmetry, but you won't have very much dissipative symmetry, and people wouldn't want to live there because there's no walls or anything. So essentially, if you make the product of these two, you get some idea of what people actually work with. And There's a paper on that in my book, which is called, let's see, somewhere here. It's called Conflict in History. There's something called Architecture, Case Study, and Transformative Factorization. And you find that for the components that are used in architecture, such as walls and pillars and so forth, there's like a local maximum of this quantity, transformity or energy. And so you have things like a wall or an empty rectangle or a pillar or something like that will have local maximum of that quantity. And you can read about that in this book, which if you want to buy it, it's $15. But anyway, it's just one little article out of that. But anyway, the last year I tried to go at this thing without having to measure this. Quite difficult to count how many sides are used up with the Lego blocks. Like if you make a castle or something like that, it's difficult to count up how many sides are actually used up when they're put together. So there's a general way of doing this thing, which I called simplexity, which is you can calculate the total amount of symmetry and just take that minus how much the structure actually has, whatever it is. And then you multiply that times the symmetry as measured that I did last year, which is based on counting the number of equal distances between pairs of points. Okay, so this is jumping around a little bit, but the question is to try to explain why you need this quantity energy or something. And essentially, you can look at thermodynamics. You find that this is from a talk called Energy to Entropy to Energy. You find that people thought that energy would measure sort of how much pep something has. But when they started studying the equations, they found out that essentially, you could have different things that have the same energy, but they have different amount of pep, so to speak. So the two cases here on the top, as long as PV is constant, the energy will stay the same because PV is dependent on the temperature, and the temperature determines the temperature according to the ideal gas law. And that will stay the same as long as PV is constant. So you can make the volume 1/16 as big and the pressure 16 times bigger, and this will have the same, these two things will have the same energy. But this one will have a lot more pep. It will bounce back, basically. So the thermodynamics people brought in this new idea called energy that's supposed to measure how tired the energy is. So even today, people don't usually talk about, they say I have a lot of energy and not that I have not very much entropy today or something like that. Anyway, so you can do these PV diagrams, and essentially the entropy is going up as you get towards the large volume down here. The entropy is going up, or the disorder. So people thought that, well, we have the answer. This is the way we can measure order versus disorder. Just calculate the entropy, and that will tell us whether we have a lot of order or not. However, that basically, so this is the second one. So there's something called Delacorte tetrode entropy. And essentially you can play the same game. The Delacorte, this is a formula for the Delacorte tetrode entropy. And this is the mass of the quantity that's in the ideal gas law. So that's taken to the 3/2 power, and V appears to the first power. So you can do the same game if you increase the mass by 16, by a factor of 16. That's like going from hydrogen to oxygen as your gas. And you take your volume down by a factor of 64, then this quantity will come out to be the same. And that means that the Sackur tetrode entropy is the same. And furthermore, because of the ideal gas law, the temperature will be the same because PV will be the same. So therefore, you have a case where you have the same energy and the same entropy, but you have a different amount of order. So most people would say that these sort of more muscular molecules of gas that are 16 times as heavier, and the volume is much less, most people would say this has more order than this. So this shows that you can't use entropy by itself to measure order or disorder. Similar to the problem that people had with energy and entropy, there's the same problem with measuring order and disorder versus entropy. Well, any questions on that?
Why do people say the one on the right has more order?
Well, because it's compressed into more space. For example, if these were Ebola patients or something, you'd much rather have them in, say, one room rather than all over the whole city or something like that. So, well, I don't know, did the list go around of the poll about which has the most order? So let's see. Actually, I've done this, and people have come out with all different ones, but it looks like the most popular one were stacked on top of each other, and like the 5 on the dice. And one of them said random. So as we'll see, there are sort of reasons for choosing each one of these. Like in the case of random, which is sort of like Bruce Lee, I forget what his statement was about the best thing is nothing or something like that. But anyway, if you look at the distribution of distances, random, everything will be there's only one distance of each type. So to that extent, the density is like a straight line, which is in some sense very ordered. But anyway, going ahead with the talk here. So any questions about this? This is kind of hard to follow at first, but what it's basically telling us is that you can't just get by with order as entropy versus order versus disorder, that you have to look for something else. So, well, I'll try to show this chart. This is from a book. I don't know how the time is coming along here. Guess we still have some time. This is from a book by Arthur M. Young. And I hope I'm not doing anything to make that noise. But anyway, he has tried to develop things into different kingdoms depending upon, well, what I claim is it's sort of like based on order. So it goes out from a very small scale, like light versus nuclear energy, atomic, chemical, sort of vegetable growth, and into animals and dominion. So anyway, my goal was to try to somehow, in terms of emergy, thinking that it could be related to building, well, emergy is sort of like energy quality. So as you go to these more complicated atoms, like from oxygen, from helium or hydrogen to say oxygen, you're getting more order in the nucleus. So and to that extent, this would be like some measure of energy as you go along here, or transformity. And it scales up also. So to go with what the actual talk was about. So anyway, there's a question of whether you can take this out of the real world into math world. And I found that you could actually do this by looking at these functions. F of x equals 1/2 times 2 plus sine of 2 pi kx. It turns out that if you measure the energy of these things in terms of the norm, the 2 norm basically squared, the different cycles all have the same energy. And furthermore, it will turn out they have exactly the same entropy. So these are functions that have exactly the same energy, you might say, and the same Shannon entropy. All of these, depending, no matter how many cycles you put in. But the Fisher information goes up. The Fisher information is defined as, let's see if I can get it down here. It's defined as, it's on the top of the screen there. It's the integral of the derivative squared divided by the probability. Anyway, it sort of measures how much the gradients are. So this is somewhat comparable to the Lego blocks. That is to say, you can use the amount of gradients to sort of measure how many surfaces are used up. If you imagine as, say, 2 particles that are defined as Gaussians, and you gradually move them together, the gradients between them will get used up, similar to the Lego blocks, sides of the Lego blocks. So, oh, the time is up. Well, anyway, let me at least try to show the final result here of this thing. So you can imagine 9 Gaussian pair pulses, and if you combine them together, the Fisher information will actually go down to a minimum because the gradients get used up. But if you keep going and decrease the separation distance to 0, the gradients will go back up, and the Fisher information will go up to exactly the same distribution or the same value it had over here. So this is one way to define energy, basically, as by the minimum Fisher information or the negative of the Fisher information. It's similar to the Lego block study.